Hi, my name is Camilo Fosco, and I'm presenting Leveraging Temporal Context in Low Representational Power Regimes, the latest paper from Olive Lab at CVPR2023. The problem that we address is that current models don't explicitly attempt to leverage temporal regularities in datasets with long videos, like the one on the right. Can we leverage the statistics in temporal sequences of video datasets to improve performance in downstream tasks? Specifically, can we build embeddings from these snippets that capture information not only about the semantics of the snippet, but also what tends to happen before and what tends to happen after that snippet? And where does this type of information help the most? To analyze this, we propose to build an event transition matrix, which is a representation that captures typical transition probabilities between actions in long video sequences. We use this matrix as supervision in a new training protocol to generate strong embeddings for video snippets. And then we leverage these embeddings to improve action recognition and action anticipation performance, especially on low complexity models. The key result is that our model agnostic framework helps low complexity models improve performance on action recognition and anticipation across 3 datasets, specifically get very good performance, training low complexity variants of moviness and X3Ds, achieving 7 and 9% increase in action recognition performance on Epic Kitchens 100. The event transition matrix that we built here is essentially a matrix where each one of its cells corresponds to an estimated probability that an action on the rows it precedes an action on one of the columns. It's computed by looking at all actions happening after a given action weighted by a certain decay function. This ends up yielding a square matrix. It's not symmetric, and we apply several post-processing steps to make it usable for our downstream tasks. Now, the way that we leverage this ETM is essentially by designing the following training protocol. We train encoders to try to solve the multitask setup of predicting the present, essentially estimating the class label of the given input snippet in the datasets that we work with. That means predicting the noun, the verb, and the noun that is being interacted with in the video. But at the same time, we attempt to train that encoder to predict the past and predict the future. That means regressing probability distributions of the events that happened before that snippet. That ends up matching columns of our ETM because of how we construct the ETM. Now, the interesting part of this is that we want to generate an embedding that captures the information from both the present, predicting the past, and predicting the future. We think that building an embedding with those 3 tasks forces it to have a rich representation that becomes really powerful for action recognition and anticipation. Building the ETM is straightforward, but we end up with a large matrix with very sparse entries. We have to apply dimensionality reduction to be able to leverage in the best way possible. We also need to be careful about the type of decay that we use to weight contributions from actions that happen much later given observation. And finally, we have to ensure that we use the right distance metric to measure the distance between action 1 and action 2. Doubling down on the distance metric, we observe 2 types of distance metrics. One of them related to frames and seconds between actions. The other one are related to the index difference in the ordinal sequence. In the first case, we essentially are in a scenario where the length of the actions affect our decay function, while in the second setup, the length of the action doesn't affect our decay value. We test all of these design choices, and we end up finding that not using decay hinders performance. Using a distance metric related to the index tends to be more performance than using time, and working with a reduced with a matrix with a reduced dimensionality tends to be more beneficial. These first experiments are done on Epic Kitchens 100, observing top 1 accuracy in predicting verb, noun, and action on Epic Kitchens with a movie net. The datasets used for the rest of our experiments are Epic Kitchens 100 with 700 videos depicting cooking actions, Ego 4D with more than 3,000 hours of video, and EGTA gaze with 10 gaze segments annotated with 19 verbs, 51 nouns, and 106 unique actions. And we mostly focus on action recognition and anticipation. In action recognition, we receive a snippet of video. We try to predict a class label, here verbs and nouns, essentially. And in action anticipation, we receive a collection of snippets or the beginning of a video. We need to predict the action that happens after that, given a certain temporal lag. Our experimental results are promising. We show that across datasets and across models, utilizing our ETM protocol is beneficial. It's crucial here that we compare always training the model without the ETM and training the model with the ETM supervision to show how the additional supervision that we introduce improves performance in action recognition. Across data sets, Epic Kitchens 100, Ego4D, and GTA, we observe strong improvements when using the ETM. Same thing happens across models. We test a large variety of models and we observe increased performance with our ETM setup. Importantly, we observe that the increased performance is larger when the model is lower complexity. The results for action anticipation are quite similar across datasets and across models to obtain increases in performance. And again, we see this trend where lower complexity models tend to gain more from using the ETM. And this is our key insight. We observe that as complexity increases, the impact of the ETM protocol tends to be reduced. But for low complexity model, this impact can be quite huge, specifically for MovieNet and X2D variants. We hypothesize that those lower complexity models struggle a little bit more at understanding the temporal regularities of a dataset during training, and supplementing with our ETM supervision helps these models improve more, even with low complexity and low representational power. Finally, we observe performance on different architecture families, and we see that on action recognition and on action anticipation, using X3D and MovieNet variants, again, the performance is larger for smaller variants, and the performance increase gets reduced when we observe variants that are a little bit more complex and have more complexity. We do specific baseline tests and ablations as well to ensure that the ETM that we build is actually the right set, utilizes the right set of decisions to achieve its performance increase. We try shuffling rows, columns, doing a full shuffle, and observing a co-occurrence matrix. Here, the co-occurrence matrix is essentially a relaxation of our current matrix where each cell corresponds to the co-occurrence frequency of action 1 and action 2. Again, we observe that using our different baselines give us the great performance, and our full setup is more performant than shuffling the matrix or doing any kind of column and row shuffling or utilizing the co-occurrence matrix. Importantly, we also test the effect of our methodology using only the past vector and the future vector. So an ablation, removing one of the types of regressions, supervisions, and we observe again the great performance if we remove those components. Our ATM shows best performance specifically for, in this case, action recognition on Epic Kitchens 100, but this effect transfer across models and across datasets. So in conclusion, we introduce this new training regime that uses external temporal regularities to boost video understanding. Using our ETM as a training target enhances action recognition and anticipation. And finally, our ETM protocol is flexible, it's model agnostic, it's cost effective, and it's easy to integrate. Thank you for listening, and for more information, visit our project page.